The derivative of a real function f at point C in its domain is defined as the limit of f of c plus h minus f of c whole divided by h as h approaches 0, provided the limit exists. The derivative of f of x at c is denoted as f dash of c, or d by dx of f of x at c, or commonly as f dash c. Thus, the derivative of f of x is defined by f dash x, which is equal to the limit of f of x plus h minus f of x divided by h as h approaches 0, provided the limit exists. Many a times, a function is defined as y is equal to f of x. For such functions, the derivative of the function is denoted by y dash or dy by dx. Differentiation is the process of finding the derivative of a function. Mathematically, we read f dash x as derivative f of x with respect to x. While defining the derivative of a function at a point C, we always emphasize the fact that the limit must exist for the existence of derivative. In the counterpart, if the limit does not exist, then we say that the function f is not differentiable at C. In other words, a function f is said to be differentiable at point C in its domain if the left-hand limit and the right-hand limit of f of c plus h minus f of c whole divided by h exists and are equal. This definition can be extended to any closed interval a comma b. A function f is said to be differentiable in closed interval a comma b if it is differentiable at every point in the interval and also at the endpoints a and b. The derivative of a function at point A is called the right-hand derivative, and the derivative at point B is called the left-hand derivative of the function. A function is said to be differentiable in open interval a comma b if it is differentiable at every point of the interval. Let's now prove an important theorem which states that if function f is differentiable at point C, then it is also continuous at that point. Let's begin with the proof. It is given that function f is differentiable at point C. This implies f dash c exists and is equal to the limit of f of x minus f of c divided by x minus c as x approaches c. For x is not equal to c, the numerator f of x minus f of c can be written as shown. Now, let's take the limit on both the sides when x approaches c. By using the algebra of limits, we can write the limit of the product of two functions on the right-hand side as the product of their limits. The limit of f of x minus f of c divided by x minus c as x approaches c is f dash c, and the limit of x minus c as x approaches c is 0. Thus, the right-hand side becomes 0. This implies the limit of f of x as x approaches c is equal to the limit of f of c as x approaches c, which is equal to the value of the function at c. Hence, function f is continuous at x is equal to c. Hence, in general, we can say that all differentiable functions are continuous. However, the converse is not always true. Let's verify this with the help of an example. Let's look at the function defined by f of x is equal to modulus of x minus 1. Observe that this function is continuous at x is equal to 1. The given function can be written as shown. Now, to check the differentiability, we have to first evaluate the left-hand derivative and the right-hand derivative at c is equal to 1 as h approaches 0. The left-hand limit of f of 1 plus h minus f of 1 divided by h as h approaches 0 is equal to minus 1, and the right-hand limit of f of 1 plus h minus f of 1 divided by h as h approaches 0 is equal to 1. Clearly, the two limits are not equal. Hence, modulus of x minus 1 is not differentiable at 1. Hence, we can say that all continuous functions need not be differentiable.